We defined a function as a collection of statements that execute sequentially. While that is certainly true, that definition doesn't provide much insight into why functions are useful. Let's update our definition. A function is a reusable sequence of statements designed to do a particular job. You already know that every program must have a function named main, which is where the program starts execution when it is run. However, as programs start to get longer and longer, putting all the code inside the main function becomes increasingly hard to manage. Functions provide a way for us to split our programs into small, modular chunks that are easier to organize, test, and use. Most programs use many functions. The C++ standard library comes with plenty of already written functions for you to use. However, it's just as common to write your own. Functions that you write yourself are called user-defined functions. Consider a case that might occur in real life. You're reading a book, when you remember you need to make a phone call. You put a bookmark in your book, make the phone call, and when you are done with the phone call, you return to the place you bookmarked and continue your book precisely where you left off. C++ programs can work the same way. A program will be executing statements sequentially inside one function when it encounters a function call. A function call is an expression that tells the CPU to interrupt the current function and execute another function. The CPU puts a bookmark at the current point of execution, and then executes, the function named in the function call. When the called function ends, the CPU returns back to the point it bookmarked, and resumes execution. The function initiating the function call is called the caller, and the function being called is the callee or called function. First, let's start with the most basic syntax to define a user-defined function. For this lesson, all user-defined functions, except main, will take the following form. Void identifier, identifier replaced with the name of your function. / your code here, #include for stdcode. / definition of user-defined function doPrint. Void doPrint, doPrint, is the called function in this example. stdcode in doPrint, \n. / definition of function main. Int main. stdcode starting main, \n. doPrint, interrupt main, by making a function call to doPrint. Main, is the caller. stdcode ending main, \n, this statement is executed after doPrint, ends. Return 0, this program begins execution at the top of function main, and the first line to be executed prints starting main. The second line in main is a function call to the function doPrint. We call function doPrint by appending a pair of parentheses to the function name like such, doPrint. Note that if you forget the parenthesis, your program may not compile, and if it does, the function will not be called. Because a function call was made, execution of statements in main is suspended, and execution jumps to the top of called function doPrint. The first, and only, line in doPrint prints in doPrint. When doPrint terminates, execution returns back to the caller, function main, and resumes from the point where it left off. Consequently, the next statement executed in main prints ending main. One useful thing about functions is that they can be called more than once. Here's a program that demonstrates this. Void doPrint. stdcode in doPrint, \n. Int main. stdcode starting main, \n. doPrint, doPrint, called for the first time. doPrint, doPrint, called for the second time. stdcode ending main, \n. Return 0. You've already seen that function main can call another function, such as function doPrint in the example above. Any function can call any other function. In the following program, function main calls function doA, which calls function dob. Unlike some other programming languages, in C++, functions cannot be defined inside other functions. The following program is not legal. #include int main. Int foo, illegal. This function is nested inside function main. std could foo. Return 0. Foo, function call to foo. Return 0. When you write a user-defined function, you get to determine whether your function will return a value back to the caller or not. To return a value back to the caller, two things are needed. First, your function has to indicate what type of value will be returned. This is done by setting the function's return type, which is the type that is defined before the function's name. Second, inside the function that will return a value, we use a return statement to indicate the specific value being returned to the caller. The specific value returned from a function is called the return value. When the return statement is executed, the return value is copied from the function back to the caller. This process is called return by value. When this program executes, the first statement in main will create an int variable named number. When the program goes to initialize number, it will see that there is a function call to get value from user, so it will go execute that function. Function getValueFromUser asks the user to enter a value, and then it returns that value back to the caller, main. This return value is used as the initialization value for variable number. Functions are not required to return a value. To tell the compiler that a function does not return a value, a return type of void is used. Let's look at the doPrint function. Void doPrint, void is the return type. std_could. This function does not return a value, so no return statement is needed. This function has a return type of void, indicating that it does not return a value to the caller. Because it does not return a value, no return statement is needed. You now have the conceptual tools to understand how the main function actually works. When the program is executed, the operating system makes a function call to main. Execution then jumps to the top of main. The statements in main are executed sequentially. Finally, main returns an integer value, usually 0, back to the operating system. This is why main is defined as int main. Why return a value back to the operating system? This value is called a status code, and it tells the operating system, and any other programs that called yours, whether your program executed successfully or not. By consensus, a return value of 0 means success, and a non-zero return value means failure. In many cases, it is useful to be able to pass information to a function being called, so that the function has data to work with. For example, if we wanted to write a function to add two numbers, we need some way to tell the function which two numbers to add when we call it. Otherwise, how would the function know what to add? We do that via function parameters and arguments. A function parameter is a variable used in a function. Function parameters work almost identically to variables defined inside the function, but with one difference: they are always initialized with a value provided by the caller of the function. Function parameters are defined in the function declaration by placing them in between the parenthesis after the function identifier, with multiple parameters being separated by commas. An argument is a value that is passed from the caller to the function when a function call is made. Do print, this call has no arguments. Print value, 6, 6 is the argument passed to function print value. Add, 2, 3, 2 and 3 are the arguments passed to function add. When a function is called, all of the parameters of the function are created as variables, and the value of each of the arguments is copied into the matching parameter. This process is called pass by value. #include. / this function has two integer parameters, one named x, and one named y. The values of x and y are passed in by the caller. Void print values, int x, int y. std_cout x\n. std_cout y\n. Int main. Print values, 6, 7, this function call has two arguments, 6 and 7. Return 0, function parameters, as well as variables defined inside the function body, are called local variables, as opposed to global variables, which we'll discuss in a future chapter. Int add, int x, int y, function parameters x and y are local variables. Int z x and y, z is a local variable too. Return z. We discussed how a variable definition such as int x causes the variable to be instantiated, created, when this statement is executed. Function parameters are created and initialized when the function is entered, and variables within the function body are created and initialized at the point of definition. The natural follow-up question is, so when is an instantiated variable destroyed? Local variables are destroyed in the opposite order of creation at the end of the set of curly braces in which they are defined, or for function parameters, at the end of the function. Int add, int x, int y. Int z x and y. Return z. Z, y, and x destroyed here. Much like a person's lifetime is defined to be the time between their birth and death, an object's lifetime is defined to be the time between its creation and destruction. Note that variable creation and destruction happen when the program is running, called runtime, not at compile time. Therefore, lifetime is a runtime property. An identifier's scope determines where the identifier can be accessed within the source code. When an identifier can be accessed, we say it is in scope. When an identifier cannot be accessed, we say it is out of scope. Scope is a compile time property, and trying to use an identifier when it is not in scope will result in a compile error. A local variable's scope begins at the point of variable definition, and stops at the end of the set of curly braces in which they are defined, or for function parameters. At the end of the function. This ensures variables cannot be used before the point of definition, even if the compiler opts to create them before then. #include. Int add, int x, int y, adds x and y are created and enter scope here. / adds x and y are visible usable within this function only. Return x and y. Adds y and x go out of scope and are destroyed here. Int main. Int x5, mains x is created, initialized, and enters scope here. Int y6, mains y is created, initialized, and enters scope here. Mains x and y are usable within this function only. std_cout add, x, y, \n, calls function add, with x equals 5 and y equals 6. Return 0. Mains y and x go out of scope and are destroyed here. In this example, all we've done is change the names of variables a and b inside of function main to x and y. This program compiles and runs identically. Even though functions main and add both have variables named x and y. Why does this work? First, we need to recognize that even though functions main and add both have variables named x and y, these variables are distinct. The x and y in function main have nothing to do with the x and y in function add, they just happen to share the same names. Second, when inside of function main, the names x and y refer to main's locally scoped variables x and y. Those variables can only be seen, and used, inside of main. Similarly, when inside function add, the names x and y refer to function parameters x and y, which can only be seen, and used, inside of add. Although passing an array to a function at first glance looks just like passing a normal variable, underneath the hood, C++ treats arrays differently. When a normal variable is passed by value, C++ copies the value of the argument into the function parameter. Because the parameter is a copy, changing the value of the parameter does not change the value of the original argument. However, because copying large arrays can be very expensive, C++ does not copy an array when an array is passed into a function. Instead, the actual array is passed. This has the side effect of allowing functions to directly change the value of array elements. We mentioned that because copying large arrays can be very expensive, C++ does not copy an array when an array is passed into a function. When passing an array as an argument to a function, a fixed array decays into a pointer, and the pointer is passed to the function. Void print size, int asterisk array. Array is treated as a pointer here. Std size of array \n prints the size of a pointer, not the size of the array. Int main. Int array equals 1, 1, 2, 3, 5, 8, 13, 21. Std size of array \n will print size of int asterisk array length. Print size array, the array argument decays into a pointer here. Return 0. A big advantage of using structs over individual variables is that we can pass the entire struct to a function that needs to work with the members. In the above example, we pass an entire employee struct to print information, by value, meaning the argument is copied into the parameter. This prevents us from having to pass each variable individually. Furthermore, if we ever decide to add new members to our employee struct, we will not have to change the function declaration or function call.